Sí, acá estoy.
No me hagas sentir culpable.
Ya. No, 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 al contrario, porque si no.
All right, we're live.
Okay.
Welcome,
Hi.
everyone. It's my pleasure to give you Nancy Sandler from Ohio University in Athens, Ohio, who's going to be talking about her latest work on photo-induced multiply quantized vortex states in Dirac like. Well, okay. Uh, all right.
Yeah.
Uh, Nancy, please take it away.
Okay. Thank you, Adrian, for the introduction. And yeah, it's a long title. And this is the first time that I will be talking about it. So I very much will be open to questions and comments. Before I start describing what this title is about, let me, oh, you're kidding me. Yeah. Let me introduce my collaborators. This is work done in very, very close collaboration with a group of Professor Mahmoud Asmar, who is at Kennesaw University, and a group of fantastic undergraduate students that did a great amount of the work that I am going to present. And I hope to be fair to their work and that you get the impression of how hard all these topics was, especially considering that they are undergraduate students. So with that said, let me tell you a little bit why we chose this topic. Well, normally when we look for new phenomenology or new physics, one way that we do that is by fabricating or trying to find new materials. And this is exemplified with what happened with graphene or the transition metal dechalcogenized, where we can make them thin and combine multiple layers and create new structures with this idea of Lego fabrication, or looking at older materials that were well known, but that had properties that were overlooked for a long time, like the case of topological insulators, that I am sure most of you are familiar with, that are insulators in the bulk, but have these peculiar metallic states on the surface, whose properties are protected by the topological properties of the bands in the bulk. Okay, so finding new materials had led us to discover new physical phenomena, but this is not the only path that we have to find new physical phenomena. Another path is to make our material system to interact with light. And this way of producing new physical phenomena is known in the field as Floquet engineering. And this is an example, for instance, of, do you see my cursor on the screen? Yeah, okay. So this is an example of a Dirac material, a topological insulator that is irradiated with a laser beam. And in the bottom, you see the image of an ARPES, time-resolved ARPES spectra, taken at different moments where a pulse of light is incident on the material. And as you see, when the light is absent, you see the typical conical structure expected from the surface states on this material. And as soon as the light pulse starts working its way through the material, we see that the band structure is deeply changed. We see a new band structure emerging with all these repetitions of this conical structure that disappears as soon as the pulse is eliminated. So light allows to modify the band structure of the material, giving us the possibility to explore regimes. This is, of course, a non-equilibrium regime, regimes that before were difficult to exploit, or regimes that we didn't have the chance to get there. Okay, and this is the motivation of our work, to see what type of new physics we can discover by irradiating light on materials. Now, in general, the general view that we have is that we have a material that is affected by the presence of a monochromatic laser, meaning one frequency, and the electron dynamics is changed because of the presence of this periodic field. Now, normally, we consider the laser to be a weak laser field, a low power if you want, and in that case, the dynamics is not pretty much modified. The band structure of the electron changes a little bit, but we still can recognize pretty much the equilibrium band structure. The populations of electrons in the states that occupy these bands also change, but this can be also thought as changes in an equilibrium distribution function, appropriate changes there. And most of the properties in this regime can be obtained using perturbation theory, linear response type of approaches. There is another regime in which the laser field is very strong, and this is the focus of this talk, in which the band structure, as I showed earlier, is very much changed, is renormalized, and people refer to these renormalized band structures as photon-dressed bands, and the electron population is redistributed in a way that doesn't happen in equilibrium. And of course, because of these strong changes, big changes, we cannot use perturbative methods to describe this. We need to use different techniques. Now, the idea that light can modify the electron dynamics in materials is not new, has been known for a long time now, and this is an example of irradiation of a semiconductor, where we see on the left-hand side the typical band structure with a gap, the plasmon frequency there when the light is irradiated in the weak laser regime. But in the strong laser regime, we see that the band structure gets gaps, openings in places where there was none before. So the idea that you can modify the band structure of the material by irradiation is not new. What is new is that now we have the disponibility of all these weird new materials and materials combinations that let us explore new phases, such as the Floquet topological insulator, the Floquet churn insulator, or rich transport regimes in which we can induce transport behavior that cannot exist in the material under equilibrium conditions. So basically what we are looking for is to dynamically control matter. And we do that with a monochromatic irradiation of a material that will produce renormalization of the equilibrium bands. We are going to talk about photon-dressed bands and the formation of Floquet block state. Now, let me stop a little bit before following to clarify more about this photon-dressed band. What I am talking here is that the bands that will appear in what we will call the equivalent to a band structure, these are bands that will contain information both about the electrons that were originally in the material and the photons with which these electrons are interacting. So that's why we talk about the Floquet block states or the photon-dressed states. Now, this irradiation can occur in two different regimes. One, we have these two elements, the photons and the electrons together. The irradiation could occur in the off-resonant regime. In this regime, the frequency of the light, the energy of the photons, if you want, is much bigger than the typical bandwidth of the material. And what that does is that the bands are never superimposed to each other. Then there is no hybridization between states belonging to different bands. And the effect of the irradiation is basically to break time reversal symmetry and introduce anomalous effects like the anomalous Hall effect in graphene. We open a gap, basically. Now, in the other regime, the resonant regime, the frequency is smaller than the typical bandwidth of the material, the region of energy that we are interested. And in that case, the driving introduces superpositions of different bands. In that superposition, we start getting states that become degenerate in energy with other states that were not degenerate in equilibrium. So we have hybridization between these states. And because of the light-matter interaction, in these hybridization points, we have gap openings. And this is what gives rise to, for instance, the Floquet topological insulator. So if you want, we have basically two regimes, the high-frequency regime, in which the effect is basically to break time reversal in the case of circularly polarized light and produce anomalous effect, open gaps. And in the resonant regime, we also open gaps, but we have gaps in places where there is mixing of states belonging to different bands. So how do we deal with this type of systems? Well, there are many different techniques, and we decided to go with the full theory, in part because we are, I think, crazy, but in part because we wanted to make sure that we didn't make any approximation that will make us reach the wrong conclusions or miss some important physics. So we decided to go with the full Floquet theory. And let me remind you a little bit about what Floquet theory states and the Floquet theorem states. So Floquet theory applies for Hamiltonians that are time periodic, and the period, of course, is related to the frequency of the monochromatic light. So we have only we are going to apply this for a light that has only one frequency. Now, what Floquet theorem states is that there is a full set of solutions for this Hamiltonian, that is this function psi of t, that can be written in a form that resembles a lot the form of Bloch states, in the sense that you have an exponential in which there is a parameter that you could have thought of the energy. Well, in this case, we talk about the quasi-energy that is labeled by two variables, L, which is the Floquet copy, and I will tell you more about it in a minute, and alpha, which are the parameters of inherited from the electronic or the material Hamiltonian that conveys all the other quantum numbers. And another part that is known as the Floquet state. The Floquet state is also periodic in time, and because it's periodic in time, we can expand it in modes. So the phi here, which has an index n, represents what is known as a Floquet mode. So the Hamiltonian, with this ansatz for the solution of the Floquet Hamiltonian, we can define an effective Hamiltonian where the time dependence, if you want, is kind of removed in a very particular way, because the effective Hamiltonian will be composed of two terms. One term is what we call the Floquet ladder, which is a diagonal term that has to do with that it's a multiple that contains multiples of integers. M is an integer there. And so depending on the number of modes that we use in the decomposition for the Floquet state is the number of, is the dimension of the matrix that we are going to end up with. And these are the elements in the diagonal. And along this diagonal, we will have 1, 2, 3, 0, minus 1, minus 2, minus 3. This is an integer, positive or negative. And the off-diagonal elements of the Floquet matrix are an integration of the time-dependent Hamiltonian in a period. So the off-diagonal give an stroboscopic, an average in time description of what's going on with the system. Now, this Floquet Hamiltonian doesn't have any time dependence, so it reduces the time-dependent problem to a static problem, with the caveat that instead of having energies representing the eigenvalues of the Hamiltonian, now we have quasi-energies that are defined up to a multiple of h bar omega. Now, to bring home the analogy between the Floquet and the Bloch approaches, let me show you these two graphs here. On the top, we have an electron, let's say, a particle that is moving, let's call it a one-dimensional potential that is periodic, and there is a periodicity in real space given by this vector r. So the potential repeats, okay? And this discrete translational symmetry, can also be seen if we Fourier transform this in reciprocal space by a repetition of the dispersion relations in momentum, with the repetition being characterized by reciprocal lattice vectors. Well, in Floquet, we have a very similar situation, except that instead of position in the horizontal axis, we have time now. And the repetition is temporal during a period t of time. Now, if I Fourier transform this, now the periodicity will appear in the energy axis with a repetition given by the equivalent of the reciprocal vector, which is in this case h bar omega. Okay, so let me give you even a more concrete example. So suppose that I have a Dirac-like material with a dispersion that is linear, described by the Dirac equation, that describes what's going on with the electrons. Now I bring the light, okay? And in my system, I need a Hilbert space that encompasses both degrees of freedom. So I need to describe the electrons and the light. And if I consider them as two separate entities, I would say I have the electrons with no photon, I have electrons with one photon, I have electrons missing one photon. And you can see that I can define, in analogy with the Brillouin zone in Bloch theorem, I can define a Floquet Brillouin zone because I have repetition after h bar omega. And that Brillouin zone can be defined between 0 and h bar omega, for instance. But in analogy with crystal descriptions, it's better to work with symmetric Brillouin zones. So we normally refer to the Floquet Brillouin zone to the Brillouin zone defined between h bar omega over 2 and minus h bar omega over 2. So this will be the points of the Brillouin zone boundaries in the Floquet space, okay? Notice that here I am talking about the electrons and the photons as two separate things that I am keeping count of simultaneously. Now, as you see in this plot, electronic states that appear when there is one photon in the system, and which belong, let's say, to this red line, and electronic states that exist when there are no photons suddenly become degenerate. And because now I am introducing the light-matter interaction, at these degenerate points, I expect gaps to open, okay? So these gaps open at the boundaries of the Brillouin zone, pretty much like what happens for electrons in a periodic potential, where the gaps open at the boundaries of the Brillouin zone in reciprocal space. So we will be focused on the physics that appears here in these gaps, in these new open gaps that appear when the light is interacting with electrons, okay? So this way of looking at light-matter interaction, as I showed you at the beginning, has been very useful to interpret these experiments of ARPEs on the topological bands on the surface of topological insulators. If you notice, we have the multiplication of the bands, the repetitions of bands when there is light there, and we can even detect the gaps, which are known as dynamical gaps, okay, from the data. This was also observed when black phosphorus was irradiated. Now, black phosphorus has an anisotropic structure, and with linearly polarized light, depending on the direction of the linear polarization, it was possible to see gap openings on the spectra or simply the repetitions of the bands, the regime where there was no hybridization, if you want. And finally, this way of thinking also helped to understand the anomalous quantum Hall effect that was produced by light irradiation in graphene a couple of years ago, which is a new transport regime altogether. So all these results have to do with irradiation with homogeneous light that you can think of as a plane wave, okay, where the whole sample receives the same amount of electric or magnetic field, and there is no special structure whatsoever to be seen. However, around 30 years ago, people started playing with structured light. And the structured light that we are interested in is related to these vortices. Now, these are images of physical vortices on water or air molecules fields. And in both cases, something that distinguishes these structures is that there is a vector field, the velocity field in this case, in which if I want to plot the vectors of the velocity field in every point, I can do it except at the center here. Here and here and here, the phase of these vectors is not defined. And as a consequence, the amplitude of the vector goes to 0. So this is pretty much the definition of an optical vortex. An optical vortex is a type of light that also is known as twisted light carrying orbital angular momentum, or vortex light, in which the electromagnetic field, and I am going to read the definition, has a single point or a line of points where the phase cannot be defined. And as a consequence, the amplitude of the electric field or the magnetic field vanishes, okay? So normally people plot the vortex light with this figure. And this figure is a little bit anti-intuitive because what the surface represents are the points in space where the phase of the electric field is the same. If you remember from the electromagnetism when you took it, that we studied plane waves, okay? Plane waves, we define the planes in which the phase of the vector field is constant, and the phase is given by the factor e to the I kz, where k represents the momentum and the direction of propagation is v. So we have these flat planes where the phase is constant. Now, these flat planes, instead of being flat planes, describe this type of screw-like surfaces. Now, if I went to plot the vector field for the electric field, let's say, what I discovered that I have two possibilities depending on the angular momentum that this, or the rotation, if you want, of this type of screw-like structure regarding the polarization of the electric field. And these are what these two things represent. When the polarization and the orbital momentum carried by this structure are parallel, the vector field has this type of structure in which the singularity point represents a saddle point, okay? Geometrically, it's a saddle point. When the orbital angular momentum and the polarization of the light are anti-parallel, the singularity, where the phase is not defined, becomes a sink or a source. Now, all what I am telling you sounds kind of, well, I hope so, as new as it sounded to me when I learned this for the first time, because first of all, I was surprised that the light could carry orbital angular momentum. I knew that the light carries spin angular momentum, one, when it is circularly polarized. Not always, only when it is circularly polarized. But I never knew that the light could carry orbital angular momentum. So when Mahmoud introduced me to this field, I was very, very surprised, kind of shocked, and I started reading about it. And I learned that practically all light sources that we work with carry orbital angular momentum. Why? Because we learned that light is represented by plane waves. Plane waves exist all over the space. As a consequence, they must carry an infinite amount of energy. However, any light source that we use, especially in labs, laser beams, they are finite in size. Now, if you want to model a finite size for the beam, you need necessarily to make a wave packet with the plane waves. And as a consequence, the electric field will have a component in the direction of propagation. It will not be a transverse wave. It will have a component in the direction of propagation. Why? Because if you go back to your Maxwell equations, to satisfy the Maxwell equation, the electric field necessarily needs to develop a component along the direction of propagation. Is the fact that we have finite size beams, which in laser physics are known as Gaussian beams, the standard, what makes the electric field not transversal, not perpendicular to the direction of propagation. And as a consequence, the Poynting vector ends up like moving around the direction of propagation, spinning around the direction of propagation. Because there is a singular point in space from which we can measure distances and direction, we find that this type of light structure carries an orbital angular momentum, and hence the name orbital angular momentum carrying light. Okay. Now, the amount of orbital angular momentum depends on the vorticity of this structure, how tightly wound is this, and of course, positive or negative for the two senses of circulation. Now, something that is peculiar, so this type of light, for instance, I learned is the type of laser beams that are used to localize particles in atomic physics. Because when you look at the diffraction pattern, we observe that this light produces a central maxima similar to any plane wave light, the standard picture that we have, but the successive maxima have regions where the light is completely absent, dark rings. So the light is only forming around these structures. And you can imagine by combining different types of laser beams with these properties, you can create potentials or regions where the light shines that have different geometrical shapes. And that's what people in atomic physics exploit many times to localize particles. So we want to play with this light, and we want to know what will this light, shining this light on a Dirac material, will do to the electron dynamics. Okay? Okay? Okay, good. So to kind of summarize, usually when we do typical light irradiation, we only use the frequency, the amplitude of the field, and the polarization as parameters to tune to modify electron dynamics. Now, with vortex light beams, we have angular momentum in addition to the spin angular momentum for circularly polarized light. So we have one more parameter here. The radial dependence is characterized with a vanishing amplitude at the origin, okay? And this is what guarantees that there will be an angular momentum L, that we call L in our work. The gauge field, the vector potential that describes such a property, is given by this expression. And I here wrote only the real part of this, okay? In this expression, epsilon sub eta refers to the polarization. So you can think of the electric field now having three components: a component along the direction of propagation, like that, and the X and Y components, if you want, in the plane perpendicular. In that plane, these two components have also the freedom to rotate circularly in one sense or the other. This is what epsilon refers to. And changing eta, we can go from circular to linearly polarized light. This is the amplitude of the field given by E0 and depends only on the distance from this singular point when the amplitude vanishes. And all the content of the orbital angular momentum is represented by this factor here. You see, normally for unstructured light, we don't have this. Now we have an angular dependence. Now, the fact that we can put all the angular dependence as an exponential factor in this form is valid in an approximation that is known as the paraxial approximation. So many times you will read about these beams as paraxial beams too. And I can talk about it a little bit later if you have questions. So what we are going to do is we are going to use this type of gauge field, okay, and make it interact with the Dirac material. So a massive Dirac material with a linear dispersion like this. Sigma represents the Pauli is for Pauli matrices that represent the spin degree of freedom of the electrons. These are spinful electrons. They are semiconductors in the sense that there is a mass separating the valence from the conduction band. And we want to see what irradiating with this type of light will do to this type of electrons, right? And we do the coupling as we always do the coupling, minimal coupling. So you can think of this as the gauge field times the current, or the density times the electric field, depending on the gauge that you work, but that's the idea. So the Hamiltonian, because of the gauge field, has the periodicity given by the light. So we can apply Floquet theory, and we can calculate the matrix elements of the effective Floquet Hamiltonian just by doing this calculation, okay? And you see that the interaction here, we have this term, which describes the dynamics of the isolated electrons, this term that describes the dynamics, if you want, of the isolated photons, and this is a term that mixes both and has this form, okay? So we said we have the Hamiltonian. Let's study the two different regimes that we can have that I mentioned at the beginning of the talk. Let's study the off-resonant regime. Remember that off-resonance happens when the frequency of the light is much larger than the bandwidth. So we are thinking of a Dirac material that has this dispersion up to a certain energy. There is a gap and there is another band up there or down there, okay? And this frequency is bigger than that. As a consequence, we can use for this Hamiltonian an expansion for high frequencies that is known as the Van Vleck approximation. And we find an effective Hamiltonian that looks like this. And if you look at this expression, the first thing that you notice, remember that eta had to do with the polarization. The first thing that you notice here is that there is nothing regarding this quantum number L, this orbital angular momentum. So basically what happens in the high frequency approximation is that the structure of the light, the spatial structure of the light, is completely gone, disappear. You can think of it happens so fast that the electrons average over the variation in the in the structure of the light, and that's why in this regime, we don't see at first order any information about the orbital angular momentum. In the resonant driving, remember it was the case when we have overlapping of bands with different quantum numbers, hybridization of states, and corresponding gap openings there for an homogeneous light, okay? These are pictures for homogeneous light that gives a special spin structure for the states in these bands. We want to see the equivalent for this when we have a light with a structure. And in that case, we will have a matrix that is gigantic. So I just wrote that matrix for what is called the one photon resonance, when I am keeping in this expression, just not to write the humongous matrix with any number of modes, I am writing it for 0 photons and 1 photon, for only 2 Floquet copies, just to show you the form that the Hamiltonian has. Again, the description of the free electron, the independent electrons, if you want, isolated. This corresponds to the isolated photon, because I have only 1 photon in this expression. And I will have this alpha 0, which represents the fact that I have 2 Floquet copies, 2 bands, okay, like pretty much in this picture. So this looks like a Pauli matrix, but now represented the 2 Floquet copies. When I have a larger Floquet space, I will not write alpha, I will write another matrix, because it will be a spinor, if you want, that will have as many components as Floquet copies in general. And again, this is the interacting Hamiltonian between the two of them, okay? For this Hamiltonian, the wave function will be a spinor that will have the 2 spin up and down components that come from the electronic Hamiltonian, and the 1-0 component coming from the 2 bands corresponding to the 2 Floquet copies. Okay, so you can imagine that as I enlarge my Hilbert space, adding more Floquet copies, this guy will have many more components, and this Hamiltonian will be represented by a larger matrix. So when we look at the Hamiltonian, we say, okay, this Hamiltonian, if I want to solve, let's say, the equivalent to the Schrodinger equation, if I want to find the wave function for this Hamiltonian, my variables, the radial and the angular variables, are coupled. So it will be great if I could propose an ansatz with using separation of variables, if I could get the angular and the radial part independent of each other. And in order to do that, we do exactly as we do in quantum mechanics problem. We say, well, let's look for an operator that commutes with our Hamiltonian, okay? And we can use those quantum numbers to represent what happens in the angular part, because this problem clearly has a circular type of symmetry. So we need to find an operator that commutes with this whole beast in such a way that we can separate the angular from the radial part and solve the equations more easily. So the first attempt is to say, well, let's take the total angular momentum for the electrons, which is in equilibrium, the total angular for the electrons, the total angular momentum will be the orbital part of the electron and the spin of the electron. So it will be the L plus S term, okay? The problem with that is that this does not commute with the total Hamiltonian, because this doesn't commute with the components that depends on the position here, okay? So we started to guess at that point that we need to extend the definition of the total angular momentum for the whole Floquet space. So we play with different proposals, and we put the condition that this operator must commute with the total Hamiltonian. And what we find is an expression that commutes with the total Hamiltonian only for circularly polarized light. And the expression for that total angular momentum operator contains the electronic part for the angular momentum, the L plus S, multiplying the identity in Floquet space, plus all this chunk that conveys the angular momentum carried by the light, the vorticity carried by the field, plus the circular polarization that comes from the circularly polarized beams. These matrices, I and F, I, F, and NF represent the identity in Floquet space, and this is a diagonal matrix where the integers cover the diagonal, and tau represents the light polarization. Now, this we we were very proud of finding this result, especially because, well, first of all, made sense, because it's like extending the L plus S to the angular momentum introduced by the number of photons that you are sending to a system. But, well, that's the expression for the quantum number of this operator. Le represents the angular momentum of the electron in this expression. But also because there were reports in the literature that stated using a different approximation, using the rotating wave approximation, and doing approximations along the way, that concluded that there was such an operator for linearly polarized light. And for us, that result didn't make any sense. Luckily, not only we can prove that this is the right result, but we also could track down in which part of the many approximations done in these papers there was the key approximation, if you want, that made the result lead to a linearly polarized light. Okay, so the conclusion is based on an approximation that is not necessarily true in general. And we corrected that in our manuscript, basically. So we consider this to be important, especially because in those papers, there are very interesting suggestions of using this light for quantum computing. And if people are going to start looking for these effects in real systems, they are not going to find it if they use linearly polarized light. So we have our humongous Floquet matrix, and we use this quantum number to propose an ansatz of solutions that separates the angular from the radial part. We end up with a set of coupled differential equations in the radial part that are as many as the number of Floquet copies that we include. So we can do calculations for different numbers of coupled equations and see how the solutions grow. And we put everything into the machine and we calculate, okay? And we plot our results in terms of the Floquet quasi-energy, okay? This is the Floquet boundary, the boundary of the Floquet-Brillouin zone, the center. The Floquet quasi-energy as a function of the electron orbital angular momentum. And we plotted the electron because this is an integer quantity, so the data look neater when you plot it. So this is a plot of the spectra for the Dirac material irradiated with light when the angular momentum carried by the light is zero. That is, this is like a plane wave. And what you see is what we call the continuum bands, the bulk bands, which are at the top and at the bottom. We have this that looks like quasi-edge states, and we see this line that is effectively the edge state that you appear, the topological edge state that you appear when you irradiate a Dirac-like material with a homogeneous light. So this was a tour de force calculation because to make sure that this is a topological edge state, we needed to discretize the Dirac equation in a way that we avoided the doubling fermion problem that is very common for Dirac equation. So this is, let's say, homogeneous light. Now we start turning on the orbital angular momentum of the light, and you see that there is this new branch that crosses the gap, in which the energy is an odd function of the orbital angular momentum with respect to the zone boundary. And when we add more vorticity to our vortices, we see that these expressions they are not symmetric, okay? So there are kinks here that are not here and there. And the number of branches that we obtain are exactly equal to the vorticity, the structure, this helix structure of the vortex beam that we put. So these are clearly new states that appear in the system, and we wanted to gain a little bit more intuition about the nature of these states, where they are located, how they look like. So we went looking for systems that also exhibit vortices, because we were working with vortex light, that exhibit vortices or have some dynamics changed by vortices in other materials. And of course, the benchmark case is the superconductors. Superconductors are, when you apply a magnetic field, in superconductors, you have these fluxes that penetrate in terms of vortices, and we find this fantastic work here, highly recommendable, where they show what happens with the Cooper pairs or the condensate in the superconductor, where you have these localized defects produced by the piercing of magnetic fluxes. So in their case, they are working with Cooper pairs, electrons will spin up and down, so they are working with 2x2 matrices. So we said, okay, let's look at our Floquet Hamiltonian in that projected regime only. We keep 2 copies just to also get 2x2 somehow to reduce our problem to a 2x2. Originally, we end up with a 4x4, but when we apply the angular momentum operator, we end up with a 2x2 matrix. So we can compare with their results. Their results are analytic and they are numeric. So we can compare how our results match in that case and see what we can learn from this mapping. So we are able to map our Hamiltonian to the Hamiltonian of an S-wave superconductor in the presence of magnetic vortices. We find, you see, this is the result of 2 coupled linear differential equations. That's why we end up with 1 quadratic. And we find the equivalence between their notation and our notation. In their case, they have spin up and spin down. We have the spin up for 1 zero copy of Floquet space and spin down for the other copy. And what we obtain from this mapping is, first of all, understand how the vorticity in the case of the superconductors determines the number of vortex states that appear inside these vortices. So the points in my branch. In the case of the superconductor, is determined by the flux quanta. In our case, the same parameter beta is determined by the vorticity of the light. So we can determine the number of vortex branches in the system to the orbital angular momentum carried by the light. Now, this mapping also allows us to obtain an exact analytic expression for the vortex core energy. So these states that we find inside the gap have an energy that is determined by this quantity, where these coefficients omega 0 and omega tilde are here, and they depend on delta, which is the structure of, in the case of superconductor, of the gap, in our case, the structure of the light in real space. And if we look, for instance, at the light with orbital momentum 1 or a single vorticity vortex, the solution for this expression gives the Caroli-de Gennes matrix solution. And this is an important result because that tells us that there are no states at zero energy inside these vortices. When we look at our numerics, we were unsure if the fact that we weren't getting a state at zero quasi-energy, it was a numerical effect, an approximation of our cutting, our humongous matrix at some point, or it was a real effect. And this expression made us sure that effectively you have a Caroli-de Gennes state with no zero energy state. Now, in order to find explicit expressions, we need to give a form for the light distribution, for the form that this vortex light has. So we put a particular formula, which is the same type of expression used in the superconducting case, and we can compare this analytic result with our numerics. And also we can compare the spacing between these points with the numerics, and we find a remarkable agreement. And we also find that in the right regimes, we have exactly the same number of vortex cores that corresponds to these expressions. So let me bring back all these ideas to our results. This is a typical result that we get when the vorticity of the light carries L equals 3. So we have different types of photo-induced states. We have localized states, which are what we call the vortex states, which corresponds to states that have this energy and this electronic angular momentum. These are 2 examples, okay, of how the wave function for these states look like. We also have another type of localized state, which is the topological edge state, with a wave function that lives outside, okay, in the boundary of the sample completely. And we have states that are delocalized, which are the bulk states, whose wave functions extend all over the system. So why do I say that these are bound states or vortex states? Why do I say that they are localized? Because if I superpose the extension of the wave function with the a spatial profile of the gauge field, you see that the amplitude of the wave function is maxima inside the region where the vortex is. So to make an analogy again with the superconducting system, in the superconductor, I can think that outside the vortex core produced by the magnetic flux, I have my standard Cooper pair, where I have the two electrons spin up and spin down, highly correlated. As the gap goes down and goes to zero because of the magnetic field flux, okay, inside the vortex structure, there is no gap. These two electrons separate, the correlation vanishes, and they two behave as if it were again independent electrons, that they are bound, okay? They are localized in this region because of the boundary conditions imposed by the magnetic field flux. In our case, outside the vortex light, we have a system in which the electrons and the photon are under irradiation of a homogeneous light. So the objects that occupy these regions are a composite of electrons and photons that are highly correlated. As the structure of the light, the amplitude of the vector field goes to zero, the correlation between these two objects disappears. They are there, I have the electron and the photon, but they are not correlated anymore, strongly correlated anymore. So this is how the analogy with the superconductor is useful to draw these analogies. So all this, as I mentioned at the beginning, is based on the condition that this orbital light has circular polarization. One could happen, okay, how robust are these results if we move away from circular polarization? In order to study that, what we did was, okay, you go from circular polarization to linear by mixing two circularly polarized light with opposite circulations. So if we have a circulation with given, let's say, anti-clockwise, represented by epsilon pi over 2 by this symbol here, I will add one with the opposite, with the clockwise, okay? But I will add this effect with a weight lambda, which will be my parameter of perturbation. As lambda increases, I will increase the mixing between the clockwise and the counterclockwise circular polarizations in order to go to the linear polarization. So basically what I am saying is I have my gauge field with the two components, and the two of them will weight equally and will describe this circle. And as I increase lambda, I will go from here to an elliptical, to another elliptical, until finally I reach, when lambda is 1, the full linear polarized regime. Okay, and the reason why these areas are different is because I want to normalize the gauge field to the same number, so I can compare systems that are affected by the same light intensity when I irradiate them. So since this is a small parameter, I can think of this as a perturbation, and I will do perturbation theory. So doing perturbation theory at first order shows me that the quasi-energy doesn't change. I need to go to second order to see how these states are mixed. And this is the expression at second order. And something that I want to point out in this expression is the fact that in the denominators, typical second order calculation, the energies that are mixed corresponds to states that have an electron angular momentum that differ by a unit of 2. So this means that odd values of LE will be mixed states that have odd values of electron orbital angular momentum will be mixed with the states that have odd values of electron angular momentum. Even values will be mixed with even values. So what I mean is, let's say I have an unstructured light, so L equals 0, a homogeneous light, and I look, for instance, at the state in the edge, one of the states in the edge, that have this particular value of orbital and electronic orbital angular momentum. This state, at second order perturbation theory, will be mixed with this and back. And all the states will be mixed, no, with the states that are 2 units to the right or 2 units to the left. And as you can see, all the states in these 2 green stripes will be mixed, okay, with the central one. And because the states in the bulk are closer in energy than these states are here, I would expect the effect to be more noticeable for states in the bulk when I start cranking my perturbation and going towards linearly polarized light. So first of all, we say, suppose that we have a small deviation from circular polarization, and you see that some states, for different values of vorticities, some states in the bulk start to pop up in the gap, but it's still very clear that we can identify the topological edge states and the vortex states. They are clearly seen still here. But as soon as I start cranking up the value of lambda going towards linear polarization, you see that the gap starts closing. And what we observe is that there is an asymmetric gap closing in the sense that the gap closes more for values of negative electron orbital angular momentum, closes faster if you want. And we also observe that pretty much the gap kills the edge and the vortex states, as it is expected when the gap collapses. The edge states, the topological edge states should disappear, and also the vortex states disappear. So I hope that I convey these main ideas here, that a structured light gives us more knobs, more tools to explore different non-equilibrium regimes in electronic systems, that in order to see localized vortex states, like those proposed in these works, and proposed to be useful for, in particular, quantum computing, the requirement is to use circularly polarized light. There is no other way, or small deviations from circular polarization. And if you have large deviations, you are not going to see anything, okay? So that's all. The end of my talk. I did the acknowledgement at the beginning, so yeah. Okay, thank you.
Thank you, Nancy, for a very, very nice work, very nice talk. Thank you. So the session is open for questions. Do you have any?
Thank you, guys.
There was one earlier in the chat. I guess they're asking what's the time resolution of ARPES, how they can resolve the.
Have no idea. Sorry. Have no idea. Come on. I am going. No, I have no idea. That's a good idea. I don't know what is the time resolution, but if you see at the figure, let's say I think that this figure is better. They definitely can identify clearly the presence of the different bands and the crossings. So, but no, I don't know about that experimental fact.
Can you say a little bit about the proposals to use this kind of
of light as well, part.
To do quantum computing?
Yeah, part of the idea is that you can generate this. So since these states are localized, okay, in a particular part of the sample, where it is? Here. These states are localized in different parts of the sample, okay? You can imagine irradiating a different part of the sample and creating these states. And you see that the separation in energy is not linear, okay? So you can target a particular range of quasi-energies or energies and isolate 2 or 3 states, use them as qubits or qubits, because the spectrum is not linear. This is something that comes from here. And the idea is that you can mimic with 2 or 3, you can create these qubits in different parts of your sample and start playing with them as you play with the transmons, let's say, normally. And the thing is, so realistically, this is a little bit problematic because, first of all, your qubit exists as long as you are irradiating. And second of all, there are all these heating effects that I didn't even mention them, that happens when you are irradiating your sample. So you need to figure out what will be the appropriate dissipation mechanisms in such a way as to not decohere the combination of these states. But yes, the proposal was kind of speculative, but the idea is that based on the fact that the spectrum is non-linear, and you can isolate particular states in different parts of the sample. So this is, yeah, sorry.
Yeah, thank you. So I got another question. So in the in the previous slide, you showed that there is a if you use circularly polarized light, you get a spin texture, right? And not in space, but in momentum.
Yeah, this type of plot. Yeah, if you
Right.
use an homogeneous structure, yeah, if you use an homogeneous structure light in the sense that the light doesn't have any spatial dependence, the spin structure that you get for this band looks like this.
Right. So what about your case?
We are working on that. Yes, we
Uh-huh.
are working on that. We are figuring out what would be, because here, the vector here is representing the spin, the electronic spin, which was a clear quantity to identify here. Now, in our case, since we have the angular momentum incorporates the presence of the photons, we are figuring out what will be the vector quantity to plot that will represent something similar to that. It's not the electron spin alone, because here we have the electron and the photon strongly coupled, okay? So is it with the Floquet copy? How does the polarization enter? Should we include the polarization in the definition of this vector? Would be the sum of these three, I don't know, the vector product. We are still trying to figure that out. What would be the right quantity to represent the equivalent to the spin structure? But yes, this is a very, very intuitive picture. No, you want to see what the heck is going on. The thing that I have in mind, that my intuition is that a full analogy with superconductors. There you have the two electrons coupled together, while here instead of two electrons, you have an electron and a photon if you want. And the problem there is that the photon is not like the electron. So how do you incorporate it, or how do you? So in other words, going back to the ARPES question, okay? These bands are electronic bands.
Right.
We automatically think that these bands are electronic bands, right? Because of the way ARPES works. But they are electronic bands that only appear when there is a photon there. Because this band, this one, let's say, doesn't exist here or here. So these bands are occupied by objects that are excited electrons, if you want, electrons that have incorporated the energy of the photon. So with the energy, it's easy to see. The question is, if I want to define a vector like the spin, should I include the spin and the polarization? Should I include the spin, the polarization, and the Floquet spinor that appears? So this is, yeah.
No, what I'm thinking, I'm thinking, off the top of my head, I don't know if it makes any sense, but I'm trying to figure out if you had a magnetic impurity in the middle of the vortex, how would it talk to the thing of the?
I have to say, we have a list of projects. This is in our list of projects. Yeah. This we just got a DOE grant, and it's in the We have too many projects. So if anybody is interested to join the group, you are more than welcome. Because there are many interesting questions. Mahmoud has been looking at Kondo with one student, with the idea of seeing if we could add that effect. I am looking at open system to tackle the issue of thermalization with these beams. So yeah, and I am serious when I'm making. If you want to join the effort, you will be more than welcome, because yeah.
We should continue the conversation offline.
Yes. Okay.
All right, everyone. If there no other questions from the audience, let's thank Nancy one more time. Thank you, Nancy, for joining us today, and thank you everyone for joining another Quantum Matter seminar. And see you next time.